Okay. Proportional control. Right. In proportional control, the response is proportional to the size of the error at the beginning. So if there's a big error at the start, there's a big full-on response. Okay. If there's a small error, there's going to be a small response by the system. Okay, we'll take this example here of a satellite dish. The dish is up on the roof. You're sitting down in the armchair. The operator turns the dial down here. There's an error of some sort when you turn the dial. The op-amp drives the driver, turns the motor turns the dish. The dish's position has been measured by some sort of position sensor. Okay? One potential position sensor is a potentiometer. So as the dish turns, the potentiometer itself gets turned. So there will be a link, a mechanical link, between the motor and that potentiometer there. Okay, mechanical link between those two. The inverting input gets the feedback signal. The non-inverting input, that's where the operator, this is the one the operator would turn, and this is the one that measures the output. The op-amp in a proportional control circuit is a difference op-amp. Difference op-amp. Okay, the output will be proportional to the difference between these two inputs. That resistor protects the bases of these transistors. It's arranged in a push-pull motor driver. When this transistor, the NPN one, when the voltage here gets to 0.7, this one switches on and current will flow from +12 down through that transistor, through the motor to 0. So the current's flowing that way through the motor. When the output here gets to -0.7, this transistor will switch on. Okay. Current will now flow from 0 down to -12. Okay, so it's going that way through the motor, different direction. The motor will spin in the opposite direction to earlier. Now, when we're using these systems, you have some you have the dish starts in this position, and the operator changes the position. The dish starts to respond. It responds fast at the start, and then it tails off as the error gets smaller and it slows down. Okay? It'll probably, if you have set it with a suitable gain, you'll still have a small error at the end, but it'll be acceptable. If you use too high a gain, the start will shoot off faster, and the system might overshoot. Go past the desired position, and it'll turn and come back. Now, if the gain's such, it might keep doing this all the time. It's called hunting. Okay, if the gain's too large, the dish itself will try to be very, very accurate, but the mechanical system will stop it, and the dish will wind up hunting. It'll just go vibrating back and forth. Right. Proportional control, the output from the system is proportional to the error. Okay, the error is just the difference between the set position and the position measured by the sensor. The two circuits you're likely to come against are this one, the position control one. The other one they use is the speed control one. To measure the speed, you can use a tacho generator. I've got a tacho generator up here. A tacho generator is analog, so it's easy to feed the tacho generator signal back into the analog op-amps. The alternative method for measuring the speed is to use a thing called a slotted optodisc. It's rather like the encoding thing inside the mice. You have a disc and there's slots cut out of it. And these slots pass, there's an infrared emitter on one side and a detector on the other. So as that disc spins, you get a digital output, and the frequency of these pulses is proportional to the speed that the shaft is turning at. So you can use that to measure the speed. Of course, this is a digital system, which is no use for the op-amp. You have to change that digital signal into a voltage before you can feed it in, making the circuit a little bit more complex. Okay? Once more, proportional control, It measures the output, and the response of the system is proportional to the error. Okay. It's the football one. This time, if you're at the goal line, you just tap it over.